Hello and welcome, honor students. I trust that you are doing well. This is our second virtual lesson inside of 14.2. The virtual lesson we had earlier this week was on Boyle's Law. In Boyle's Law, we learned about the relationship of pressure to volume and that it was an inverse relationship. Today, we're going to learn about Charles's Law. So a couple things before I get started. I posted a link in Moodle for you, and it was a formula sheet. Please take an opportunity to print that formula sheet. That is very important. You'll be able to use that on your test for this chapter. And it's very helpful as you do these worksheets to have it handy so you can look at these particular formulas. So we learned about our Boyle's Law formula, P1V1 equals P2V2. Today we're going to learn a little bit of a different formula. It's Charles's Law. Please do make sure you take the opportunity to watch these virtual lessons, maybe pause them and fill in some notes, particularly vocabulary, and also take an opportunity to pause them and work out some of these problems. It's a great opportunity for you to practice them in a safe environment of your notes rather than on a test or a quiz. So let's get started. So Charles's Law, key concept. How are the temperature and volume of a gas related? That's what we're going to learn about today. So this particular section, the gas laws, I had, and it's a shame that we're not meeting together. I had a really nice lab that I had laid out. Actually, there was several labs that I had planned for this particular chapter. But unfortunately, we were not able to accomplish that. But one of them was this right here where you're looking at. We were going to take some ice water and some hot water and have some balloons. And we have an opportunity for you to measure the circumference around the balloon, and then you would stick it into the ice water. And then you'd measure it after about 30 seconds. Then you'd repeat that. Take another balloon, get the circumference, stick it into the boiling water, hold it into the boiling water, and then after 30 seconds, take it out and then we measure the circumference around. And you should have noticed something happened. So this is what this is talking to us about here. So if you dip in liquid nitrogen, which is about 77 Kelvin, very cold, the air inside cools rapidly. So if the temperature drops rapidly, the kinetic energy of the particles falls. So if the kinetic energy falls, it's not going to be striking the walls of the balloon or container with as much force. So therefore, the volume will shrink. And that's what's talking about here. Conversely, if you put it in hot water, it's going to take some of that energy. The molecules are going to be moving faster, striking more rapidly. So now it's going to increase. The pressure will go up. So you're holding the pressure constant in Charles's Law. So the only way to manage that is the volume must increase so the pressure stays constant. All right, as the temperature of an enclosed gas increases, the volume increases if the pressure's held constant. So we have a relationship. So as the temperature goes up, the volume goes up. As the temperature falls, the volume falls. So we have a direct relationship here. But you have to have the pressure has to be equal. Pressure is equal. It has to be constant. And N, I'll just put N there, that has to be equal. So N is moles. So you can't add any more gas to it. So it has to be the same amount of gas that you started with. So pressure and moles are constant. So it is a direct relationship between temperature and volume. And here's our formula. So if you print that formula sheet, you'll have it in front of you. You still might want to write it in your notes so that you have it there and you have a definition here. So Charles's Law states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure is held constant. A couple of things, vocab term, please write that down. Kelvin temperature. Your temperature must be Kelvin. A lot of these problems just give you straight Celsius, degrees Celsius, degrees Celsius. You have to convert. So you must be in Kelvin. And to get to Kelvin, you have degrees Celsius plus 273. And that equals Kelvin. So that is just a quick reminder on that. And your formula here, V1 over T1 equals V2 over T2. One of the things I like to teach students is to write it out and cross multiply. Cross multiply, and then you can easily account for all your variables, and it doesn't matter if it's in the numerator or denominator because you put it in a straight line. So how do you do that? Cross multiply like that. So I would go V1 T2 equals V2 T1. And you're going to notice I'm going to do that as I work these problems. It makes it so much simpler. Just isolate what you're solving for and plug in the units that are given to you. One of the key things in solving these problems is you'll notice either it does not say anything about pressure, or it tells you pressure is constant. That's how you know you're dealing with Charles's law. All right, now we're looking at a graph. If you remember when we looked at Boyle's law graph, I'm gonna put it right here on the side, we had pressure to volume. So as the volume decreased, the pressure increased. So you had this curved line, really important. Hopefully you jotted that down in the last virtual lesson. But today, let's look at Charles's law. So we have volume and temperature. So let's look at what happens here. As the temperature goes up, the volume increases. That's what we see happen. And as the volume decreases, the temperature decreases. So it's a direct relationship, and it's a straight line. That's a great type of a test question. How are the lines different between Boyle's and Charles's law? And we're going to learn the next one, Gay-Lussac's law, on Tuesday when I do the post-virtual lesson for that. But we have a curved line for Boyle's law, and we have a straight line for the relationship of volume to temperature because it's direct. Pressure volume is indirect, curved line. Volume to temperature direct, straight line. Very important. All right, hot air balloon. So a hot air balloon has a burner on it, and they keep heating the air inside. So when they heat the air inside, the molecules are going to be bouncing back very rapidly, thus expanding the volume. So the volume should be going up, and that is exactly what they tell us here. The volume of the balloon increases. So let's look at an example problem here. So a balloon inflated in a room at 24 degrees Celsius has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees. What is the new volume? So first thing you always want to do is write down all your variables. And that's what they've done here. They write down everything that's given, and that way they know right here, I'm solving for my V2. Please don't cut a corner on that. That's really important to write down everything. Then you gotta remember convert to Kelvin, got to be in Kelvin. So that's our next step. And you see they've done that here. They've converted to Kelvin. And then they just simply manipulate the formula. As you see here, they isolated that they're solving for V2, and then they just plug in. And they plugged in all their information, and they come out to 4.46 liters. All right, let's take a look at this quick problem here. So what is the temperature of 2.3 liter balloon? So we have here, I'm going to start writing down my variables. So it says temperature 1 equals blank Kelvin. I don't know what that is, but I do know my volume 1 equals 2.3 liters. It says if it shrinks to a volume of 0.632 liters, so my volume 2 equals 0.632 liters. And my temperature 2, it gives it right here to me, liquid nitrogen, 77 Kelvin. So notice there's no mention, there's nothing mentioned of pressure, so that means it has to be constant. So now I'm going to write my formula here. So I have V1 over T1 equals V2 over T2. So I'm going to cross multiply. So I have V1 T2 equals V2 T1. I simply cross multiplied like that. I'm solving for T1, so I'm going to divide both sides by V2. It cancels, and that isolated my temperature one, and that's what I'm solving for. So now I'm just going to simply plug all my stuff in here. So my volume is 2.3 liters, parentheses. My temperature 2 is 77 Kelvin, divided by my V2, and V2 is 0.632 liters. My liters cancel, and that leaves me in Kelvin, and that will be my temperature. So I'm going to plug this in, 2.3 times 77 divided by 0.632. So, all right, I have to be at two significant figures. So I'm going to have 280 Kelvin. So I can come up here and write it 280 Kelvin. So let's see what they do. They kept it at three significant figures, but it should have been at two. So 276 would have rounded. If you do properly, you have two sig figs. So that's actually incorrect. It should be 280 if you round it. Please don't forget significant figures. I've been trying on your daily work that you've been posting in, making little notations. So please go back in and look at some of these assignments and see the notations I've written on them in Moodle. All right, so let's look at a couple other problems here. So a container holds 50 milliliters of nitrogen gas at 25 degrees Celsius and a constant pressure of 736 millimeters of mercury. What will be its volume if the temperature increases to 35 degrees Celsius? All right, so right away, just reading this, constant. I'm not having to worry about pressure. So that right away triggers to me, this is Charles's law. So I have V1 over T1 equals V2 over T2. So now I can write down all my information. So my volume 1 equals 50.0 milliliters. And milliliters are fine. You don't have to be in liters on this. My temperature 1 equals, it says 25 degrees Celsius plus 273 equals. So I have to be in Kelvin. So this comes out to 298 Kelvin. So then it says here my V2, and that's what I'm solving for, blank milliliters. And my temperature 2 is going to equal, right there, 35. So 35 degrees Celsius plus 273 equals. So I have 308, if I did the math right, 308 Kelvin. So now I can manipulate my formula. So I have V1 T2 equals V2 T1. I'm solving for V2, so I'm going to divide both sides by T1. That cancels off, and that gives me my volume 2. Now I'm simply going to plug in my variables that I have written down. So I have 50.0 milliliters. My temperature 2 is 308 Kelvin. I'm going to divide that by my temperature 1, which is 298 Kelvin. So Kelvins cancel, and that will equal my volume 2. So I'm in milliliters. So I go 50.0 times 308, and I'm going to divide that by 298. So I need to have three significant figures. Everything I have is in three significant figures. So 51.7. So my V2 equals 51.7 milliliters. So I can come up here and write that down. 51.7 milliliters. So let's look at it. It went up from 298 to 308, so the volume had to go up as well. So it went from 50 to 51.7. So it is a direct relationship. So that is your answer on this particular problem. I have another problem here for us. Why don't you pause the video for a second, work this out in your notes, and then pop back on and see how I solved it. All right, so let's take a look. A sample of hydrogen has an initial temperature of 50 degrees Celsius. When the temperature is lowered to -5 degrees Celsius, the volume of hydrogen becomes 212 centimeters cubed. Remember, that's equivalent. 1 centimeter cubed is 1 milliliter. So it would be similar to writing 212 milliliters, but this gives us centimeter cubed. We'll just keep it in centimeters cubed. That is a unit of volume. What was the initial volume of the hydrogen? There is no pressure mentioned. It is only dealing with volume and temperature. So this is Charles's law. So I can go V1 T1 equals V2 T2. So I'm going to come over here and write down all my information. So my volume 1 equals blank centimeters cubed. I'm just going to write it down. It's what it's asking for. So my temperature 1 equals, and it says here 50 degrees Celsius. I have to convert that. I like to convert right away. So that way I don't have to worry about forgetting. So I'm at 323 Kelvin. So then my volume 2 is going to equal 212 centimeters cubed. And my temperature 2 equals, and it says -5 degrees Celsius plus 273. So that's going to equal 268 Kelvin. All right, so now I'm simply solving for V1. So I'm going to cross multiply. So I'm going to go V1 T2 equals V2 T1. So I'm going to get rid of the T2. So I'm going to divide both sides by T2, and that cancels off. So now I can plug in. So V2 is 212 centimeters cubed. T1 is 323 Kelvin. I'm going to divide that by my T2. T2 is 268 Kelvin. Kelvins cancel. That leaves me in centimeters cubed. That's a unit of volume, and that's what I'm solving for, volume 1. So I go 212 times 323, and I'm going to divide that by 268. So, and I have to be at 3 significant figures again, 3 significant figures. So it comes out on my calculator to 255.5, so that's 256 centimeters cubed. So I can come over here and write that down, 256 centimeters cubed. Now let's make sense of this. So I had a volume and a high temperature. The temperature fell, and notice what happened to my volume. My volume directly fell. So it went from 256 to 212. So ladies and gentlemen, that's how you utilize Charles's formula, Charles's law formula, in solving problems dealing exclusively with volume and temperature when you're holding pressure and the moles of gas constant. So that is this particular section. I have a worksheet that I posted on Moodle that'll be due Tuesday, upcoming Tuesday at 8:00 p.m. So please take a look at that and try the practice on that. Tuesday, the 14th, I will have another virtual lesson, and it will be on Gay-Lussac's law. And we will talk about that next week. So go in peace. Enjoy your Easter Sunday and your family and the time off. And we'll see you back on Tuesday. Go in peace.